Hello there, Miss Barber here. This lesson is titled Exponential and Logarithmic Equations. As the title suggests, in this lesson we will solve equations that involve both exponential and logarithmic equations. The techniques you develop in this lesson will equip you to solve applications that require these functions. With that said, the learning objectives of this lesson are: 1. Be able to solve exponential equations. 2. Be able to solve logarithmic equations. And 3. Be able to solve applications involving compound interest. Roman numeral 1. Exponential equations. An exponential equation is one in which the variable occurs in the exponent. Remembering that exponential functions and logarithmic functions are inverses of each other, the following are guidelines for solving exponential equations. Number 1. Isolate the exponential expression to one side of the equal sign. 2. Take the logarithm of both sides, then use the laws of logs to relocate the exponent as a coefficient. And finally, 3. Solve for the variable. Solve the following exponential equations. Part A. 10 to the power of 2x minus 3 quantity equals 1 over 10. Let's rewrite this. So we'll have 10 to the power of 2x minus 3 is equal to, and 1/10 can be written in exponential form as 10 to the minus 1. Now the bases are the same. The equations are set equal to each other, so we can just solve for the exponents. That is 2x minus 3 equals negative 1. Let's add 3 to both sides, so negative 1 plus 3 would end up giving us, what is that? 2. That was embarrassing. And if I divide by 2 on both sides, I get x equals 1. And check it. Put in x equals 1 into the left-hand side of the equation. Make sure that you get the answer that we need. Let's go to part B. 2 times e to the power of 0.4x equals 16. The guidelines say isolate the exponent first, so let's divide by 2 on both sides. Then we get e to the power of 0.4x equals, and 16 divided by 2 is 8. Use whatever log you want to, but it is standard and customary to use ln for e and the common log for base 10 if you have to take the log. So let's take the natural log of both sides. The natural log of e to the power of 0.4x equals the natural log of 8. The rules, the identity rules, tell us that ln of e to whatever a power is actually just that power. So 0.4x equals the ln of 8. And then divide by 0.4 on both sides. So you get x equals ln of 8. That is a number by itself divided by 0.4. This is called the exact answer. Now, if you want a decimal approximation, then you'll need to use your calculator. This is the screen of a TI-84 CE calculator. To compute the ln of 8 divided by 0.4, find the ln button on your calculator. It lights up as red. 1/8, and close the parenthesis. Now we want to divide the entire expression by what was our divisor, which was 0.4. Then the output you get is 5.198603854. So we would write, this is the exact, this is as far as you can go without a calculator, and the approximate is the decimal representation, and we would have x equals 5.19860. Let's continue. Part C. 1 plus 3 to the power of 4x plus 1 quantity equals 19. The rule is we have to isolate the exponent, so let's subtract 1 from both sides. In doing that, we will get 3 to the power of 4x plus 1 equals 19 minus 1 is 18. Now take whatever log you want to. The recommendation is always use either the common log or the natural log. For variety, let's use the common log. Then I would have the log of something is equal to the log of the other thing. And let's put in the expressions 3 to the x, 4x plus 1. The value in rewriting this exponent as a logarithm is now we can take the power that has the variable in it and make it a coefficient. So then we have 4x plus 1 parenthesis times log 3 equals log of 18. Distribute the log 3. So you'll get 4x times log 3 plus 1 times log 3 is just log 3 equals log 18. Now we need to get x by itself, so let's subtract the log 3. So we'll have 4x log 3 equals log 18 minus log 3. Now, the properties of logs lets us say that this is actually the log of 18 divided by 3. So now we'll have 4x log of 3 equals the log of 18 divided by 3 is 6. And let's solve for x. X would be the log of 6 divided by 4 times log 3. And this is exact. Part D, e to the x plus 15 times e to the minus x minus 8. So we're going to have to do some simplifying before we can proceed. Let's write this as e to the x plus 15 divided by e to the x, because the minus x lets us put it in the denominator, then minus 8 equals 0. Now this doesn't look real friendly, but e to the x is a non-zero number, so to solve this problem, you know what? We're just going to multiply through by e to the x. Then when you distribute this new e to the x, we'll get e to the 2x plus 15 minus e to the x equals 0. The reason we only have 15 is that the factor of e to the x we multiply through cancel the denominator. Let's change the order a little bit and you get e to the 2x minus 8 times e to the x plus 15 equals 0. That is a quadratic type. We can factor this as e to the x times e to the x. We'll set that equal to 0. The factors of 15 that work to give us 8 would be 3 and 5, so minus 3 and minus 5. Using the zero product property, we get that e to the x equals 3. And for the second one, we'll get that e to the x equals 5. Now, using an identity property of the natural log, solving for x would give us, for e to the x equals 3, x equals ln of 3. And for e to the x equals 5, we'll get x equals ln of 5. And these are called exact solutions. Roman numeral 2, logarithmic equations. A logarithmic equation is one in which a logarithm of the variable occurs. Guidelines for solving logarithmic equations are as follows. Number 1, isolate the logarithmic term to one side of the equal sign. You may need to combine the logarithmic terms first. 2, write the equation in exponential form or otherwise raise the base to each side of the equation. And 3, solve for the variable. Solve the following logarithmic equations. Part A, 12 times the natural log of the quantity x plus 5 minus 2 equals 22. The process is, if there's no logarithms to combine, then begin by isolating the natural log. So we'll begin by adding 2 to both sides. Then this equation becomes 12 times the natural log of x plus 5. And adding 2 to both sides, 22 plus 2 is 24. Now, again, we're still trying to get the natural log by itself, so divide by 12 on both sides. And this will give us the natural log of x plus 5 equals 24 divided by 12, or 2. We rewrite this. If you have an unknown in the log, you're going to have to use exponents. If you've got an unknown in the variable, you're going to have to use logs. So we are going to rewrite this in terms of an exponential expression. Just a quick reminder, the natural log is exactly the same thing as log to the base e. So if you have log to the base e of the quantity x plus 5 equals 2, we can rewrite this in strict exponential form, and we would get e squared equals x plus 5. Then you can solve for the x by itself, and you'd have e squared minus 5 equals x. So our answer is x equals e squared minus 5. This is exact form. An approximation requires you to key these numbers into a calculator. Part B, log to the base 3 of quantity x plus 15 minus log base 3 of quantity x minus 1 equals 2. The two logarithms on the left-hand side will require us to use the laws of logarithms to combine. So we will combine this as log base 3, and then the argument of the first term, that's x plus 15, divided by the argument of the second term, x minus 1, equals 2. We still have the unknown within the argument of the log, so we will rewrite this as an exponent. That is, we'll write the base, which is 3, squared, equals the rational expression, x plus 15, divided by x minus 1. Now, this is in a form that we can solve. We would write that 3 squared is 9 equals x plus 15 divided by x minus 1. Let's multiply the denominator through, and so we'll have 9 times the quantity x minus 1 equals x plus 15. Now distribute the 9 on the left-hand side, so you'll have 9x minus 9 equals x plus 15. And then we solve this linear equation. I'll subtract x from both sides, so 9x minus x is 8x. Then add 9 to both sides, so 15 plus 9 is 24. We can solve for x by dividing by 8 on both sides, and 24 divided by 8 is 3. Roman numeral 3, compound interest. Let's recall the financial interest formulas. First one is simple interest, written as A equals P times the quantity 1 plus R. Notice that T is missing for time. This is a simple interest formula good for only 1 year. 2. Compound interest is A equals P times the quantity 1 plus R over N, all raised to the power of N times T. Remember, A is future value or account balance. P is principal or present value. R is interest rate expressed in decimal form. N is the number of compoundings per year, and T is time in years. And finally, 3, continuously compounded interest, given as A equals P times the number E raised to the power of RT. I'd circle that and make a note of it because it is exactly the same format we use for exponential growth. A sum of $5,000 is invested at an interest rate of 5% per year. Find the time time required for the money to double if the interest rate is compounded, part A, semi-annually. Semi-annually tells us we are looking at a compound interest problem, so we'll use the formula A equals P times the quantity 1 plus R over n to the nt, and we need to identify the parts. We're not quite told what A is. The principal is 5,000. The rate is 5%, so we'll write it as 0.05. The number of compounding semi-annually means twice a year. Time is what we're looking for. So our conundrum right now is what to do with the value for A. We want it to double. So if you started at $5,000, then the result would be that you want $10,000. So let's set this up. We'll have 10,000 is equal to 5,000 times 1 plus 0.05 divided by 2 raised to the power of n, which is 2, and t, the value we're looking for. In solving this exponential expression, we need to get the exponent part by itself, so let's divide by 5,000 on both sides. Then we get 2 equals 1 plus 0.052 to the power of 2t. Notice we really didn't need to have any amount of money at all. A would be 2, P would be 1 if we're looking to double the investment. Now let's compute, and we'll get 2 equals 1 plus 0.05 over 2 is going to be 1.025 to 2t. To solve for the unknown in the exponent, we'll need to take the log of both sides. You can use any log you want to, but you should choose either the natural log or the common log because those are the function values on your calculator. For this problem, I'll just pick natural log. So I will have the natural log of 2 is equal to the natural log of 1.025 to the power of 2 times t. Now we'll use the properties of logarithms that lets us move the exponent into the coefficient. So you have the natural log of 2 equals 2t times the natural log of 1.025. Now divide the 2 and the natural log of 1.025 to get the t by itself. So you have the natural log of 2 divided by the quantity 2 times the natural log of 1.025 equals t. Okay? That really tells you nothing, so let's compute that value in your calculator. On the calculator, let's find the natural log button, which would be ln. Then we need 2. Let's close that. Then I'll divide that by, I'm going to go ahead and put parentheses around it, make sure we keep it together, 2 times the natural log 1.025, and we'll close, press enter, and we get 14.03551726. Let's round that to the nearest year and a couple of decimal places. And we'll say that doubling time at 5% compounded semi-annually would be 14.04 years. Now let's answer that question for part B, continuously compounded interest. Continuously compounded, we're going to use the formula A equals P e to the RT. Okay. If we put $1 in the account as a starting point, when you double it, you want $2. You get the same thing if you put 5,000 in for P and 10,000 for A. When you divide, it's still going to be the numbers 2 and 1. E raised to the power of 0.05t. That's kind of messy, so let's clean it up and we'll write 2 equals e to the 0.05t. If your base is e, use the natural log. If your base is 10, use the common log. If your base is anything else, use whatever makes the problem easiest to work. So if we take the natural log of both sides, then we get that the natural log of 2 is equal to, and the natural log of e raised to anything is just what that anything is, so it'll be 0.05t. Solving for t, we get ln of 2 divided by 0.05 equals t. Now that's an exact number and it has no meaning for us if I want the time, so let's go ahead and compute that in our calculator. We need to find the ln function on the calculator, which is right here, ln, and we want to divide it by the interest rate, which was 0.05, press enter, and the output is 13.86294361. So let's write that on our answers. We have that at continuously compounded, okay, the time to double is roughly 13.86 years. And if it's semi-annually, then the time to double is 14.04 years. Why does it take less time to double if it's compounded continuously as opposed to compounded semi-annually?